Hi students, today we are going to see about stable and unstable systems. Stable and unstable systems. In the previous class, we saw the systems static and dynamic, causal and non-causal. So I explained you about static and dynamic systems, causal and non-causal system in the previous class. Now today's class I am going to explain you about stable and unstable systems. Stable and unstable systems. So first of all, what is a stable system? Which system is called as stable? Stable system. So here a system is said to be stable. A system is said to be stable only if the bounded input produces a bounded output. If the bounded input produces a bounded output, that is, whenever a bounded input produces a bounded output, then I can say that system has a stable system. Here the bounded input, bounded output. There is a new term, bounded. So I will explain what is bounded. Okay. Now here first I am going for the definition. Definition of stable system. A system is said to be stable whenever a bounded input produces a bounded output. So that is we call that as BIBO stable. BIBO, B-I-B-O, stable. Bounded input, bounded output stable. That is simply BIBO, B-I-B-O stable. B for bounded, I for input. B for bounded, O for output. BIBO input. So that is bounded input, bounded output stable. BIBO stable. Clear? Now, in the same way, which system is called as an unstable system? Which system is called as an unstable system? Simple. For a bounded input, if the output of the system is unbounded, then the system is called as unstable. Or simply, a system is said to be unstable. if the bounded input produces an unbounded output. At least for one bounded input, if it is producing an unbounded output, then that system is nothing but unstable system. Okay. So a system in where the bounded input produces a bounded output, that is stable. If the bounded input produces an unbounded output, then that is an unstable system. Simple thing. So for at least one bounded input, if the system is producing an unbounded output, then that system is an unstable. Or simply, for a bounded input, if the output of the system is unbounded, then the system is said to be unstable system. So here we have, whenever anyone asks you what is a stable and what is an unstable, if the system produces a bounded output for a bounded input, then it is stable. If a system produces unbounded outputs for a bounded input, then that is unstable. Okay. Bounded output for a bounded input is nothing but the stable system. That is the BIBO stable. In the same way, unbounded output for a bounded input, that system is nothing but unstable system. So here a term bounded. What is a bounded signal, or what is meant by bounded? Simple. For a bounded signal, if you say that signal as a bounded signal, its magnitude or amplitude must and should be a finite one. For a bounded signal, its amplitude or magnitude will be a finite value. That is, a signal whose magnitude or amplitude is a finite, then we can treat that signal as a bounded signal. So it should be in the limits. Bounded, it should be in the limits. That is simply the magnitude of the signal should be a finite value. Remember, bounded signal means the magnitude of the signal. Should be a finite value. That is bounded within the limits. That is, it should not be infinite. It should not be infinite. If the magnitude of the signal, is not a finite, that is, if the magnitude of the signal is infinite, then simply it is unbounded. Simply it is unbounded. Is it clear? Simple. Here only the bounded signal is whenever the magnitude of a signal is a finite value, then we can say that signal is a bounded signal. Bounded signal means the magnitude of the signal should be a finite value, less than infinity. Okay. And unbounded, if the magnitude of the signal should be an infinite, then it is not a finite value. It is not a finite value. The magnitude of the input signal, the magnitude of the signal is not a finite value, then you can say that is an unbounded. So for that, for a bounded signal, I will give you an example. Sine wave. So here the sine wave amplitude. Okay, consider a sine wave. See, so this is the maximum amplitude and this is the minimum amplitude. Okay, here for the sine wave, the amplitude or the magnitude of the sine wave is finite. It is finite, so it has some limits. So it's a positive value, it is the negative. Okay, so it has a finite value. So general sine wave, the sine function will have a maximum value of 1 and will have a minimum value of -1. So for sine wave, so it should be +1 to -1. That is the sine function. The sine function, anything, sine of anything, the sine function will have a values between +1 and -1. So between these two, okay, it will have the values. So sine function, so or -1 to +1 or +1 to -1 in between this one. Okay, you can write this one. So the sine function will have values from -1 to +1. Clear? So that is, here the amplitude or the magnitude of the sine function is a finite value. So we can say that sine wave is a bounded signal. Sine wave is a bounded signal. Okay, bounded signal. I can give you another example for the bounded signal. See, this one. This is bounded. This value is a finite. The amplitude of this one is a finite value. So that is also an example for bounded signal. So this one is also an example for bounded signal. Or see, yeah, this is also an example for bounded signal, because here the amplitude is constant as a finite value. The amplitude is, let us say this is 5. The 5 value is constant. So here also the amplitude of the signal is constant. So you can say, treat this as also a bounded signal. Okay, so we have so many examples for bounded signals. This is also a bounded signal. Now come to unbounded signal. Can you give some examples for unbounded signal means? So I can give the examples for unbounded also. So there it is increasing. The amplitude should do increase. So it will go on. Okay, let us take increasing sine wave. See, so this will be an example for unbounded signal. Or you can go for an increasing exponential. Yeah, so these are also the examples for unbounded, because it will go on. Unbounded signals, or a ramp signal, or you can go for a ramp signal. So these are all examples for unbounded signal, because their amplitudes goes on increasing. That is, they are not having a finite values. So the magnitude of this will be an infinite value. So for that reason, so you can treat this as unbounded signals and we can treat this as bounded signals. Okay, so I had given the examples for bounded, I had given the examples for unbounded. And let us take for signal, this is the input, and this is the output. For this input, it is producing output like this. Okay, this is input, this is output. Both are bounded. Input is a bounded one and the output is also a bounded one. Then I can say this system as Bebo stable system, bounded input, bounded output, stable system. This is a stable system. If for the same input, if it is producing the output like this, it is producing output like this, the output is this one. The output of that one is this one. So this is the output for this one. This is the input and this is the output. Then input is bounded, but the output is unbounded. Output is unbounded. So for bounded input, it is producing an unbounded output. Then we can say that as unstable. So this system we have to say as unstable, and this system we have to say as stable. So this is a stable system and this is an unstable system. So I hope you all have a clear idea. So this is the graphical representations for explaining stable and unstable. So you can go for the equational format also. Okay, so in the next slide we will see that one. Yeah, see now stable and unstable systems. So I will go for the equation format. I will explain that one. Like consider the input signal x of t be bounded. So whatever the input I am taking, I am considering that as a bounded. Bounded means its magnitude is a finite value. Magnitude is a final value. So for that reason, I have written the magnitude. Okay, I have written the magnitude. Mod of x of t is less than or equal to mx, whose value is less than infinite. Simple. That is, here I am considering the signal as x of t, which is a bounded. That is the magnitude. Of that value should be an finite value. So I have taken mx is a positive real number. There is a finite value which is less than infinity for all values of t. That x of t, the magnitude of that x of t is either less than or equal to mx, where mx is a positive real number and that value is less than infinity. That means here the magnitude of that as input signal is a finite value which is less than infinity, and I treated that as an mx. So I can say that as a bounded input. Okay, now if I give that to a system, and if that system output, okay, and if that system output y of t, magnitude of the system output y of t is also less than or equal to a constant my is also a real positive, okay, positive real number, and that value is less than infinite, and this value is less than infinite, okay, less than infinite, then we can say that output is also a bounded, because the magnitude of the output signal is also a finite value. That is, the output is also bounded. If the magnitude of the output y of t is less than or equal to a positive real number my, which is less than infinity, then I can say that output is a bounded. That is, for a bounded input, it is producing a bounded output. Then the system is said to be Bebo stable. Otherwise, we can say the system is unstable. Clear? So in this way also we can explain a stable and unstable system. So here I first of all had taken an input signal as x of t, which is a bounded one. For that I had represented, bounded means its magnitude should be a finite value. For that I had taken mod of x of t is less than or equal to mx, a positive real number which is less than infinity for all t, and I had given to a system. And if the system output is the magnitude of the output is also less than or equal to a positive real number my which is less than infinity for all t, then I can say the output is a bounded one because it is a finite value. So the output is a bounded one, and that is a finite value. As it is a finite value, it is a bounded one. Then we can say the system is BIBO stable, bounded input, bounded output stable. Otherwise, we can say the system is unstable. That is, if the output is not a positive real number and it is not a less than infinity, that is, if the output is infinity, it is infinite. For a bounded input, if the output is an infinite, that is not a finite value, the magnitude of that output signal is not a finite value. For not a finite value means infinite, then I can say that system is an unstable system. Can say that system as an unstable system. Okay, so here I explained graphically. Here I am explained with some equation format. So for your better understanding, I had shown the two variations. So this is the explanation for stable and unstable systems. Stable and unstable systems. So I will show you the graphical formats. Okay. Now graphical examples for this one. I hope you are clear with this one. Okay. Whenever if the input signal, magnitude of the input signal is a positive real number which is less than infinity, that is, it is a bounded, and it is producing an output whose magnitude is less than or equal to my, that is less than infinity, is also a finite value, that is also a bounded, then I can say the system is a BIBO stable. If it is not satisfying this one, that is otherwise, if the output is an infinite value, not a finite value, then we can say otherwise the system is unstable. Okay. Now graphical representation examples. Already I shown you there. I shown you here all the graphical examples. Again, I am giving you these graphical examples. Okay. So there, first I had taken the input. Okay. For that input, the output waveform is a decreasing one. It increases up to the top and then it's slowly decreasing. So this is stable. And see, for the same input, if we have a format like that one, the last one, so it is also stable. So come to downside, the first one of the second row, so that is a marginally stable. Okay, marginally almost stable. And see the fifth, that is in the second row, the second one for that input, for the given input, the output is increasing exponential, which is having an infinite value. So that is unstable. And the last one, see the last one. For the last one also, it is increasing, sinusoidally increasing. So it will go upon to infinity as the time increases. As the x increases, it will go upon to the infinity. So that is also an unstable. Here input is stable, constant. For the input, we have different types of outputs. First one is the input, the second one is one type of output, the third one is another type of output, and the fourth one is another type, fifth one is another type, sixth. We have different types. Okay, for the single input, I had given 5 outputs. So based on that input output combination, I can say whether it is a BIBO stable or unstable. So for the given input, the second one and the third one of the first row, are the stable examples because they are examples for stable signals. So signal is like this. It is decreasing to 0. It is a stable one. And it is producing some constant value. It is also stable one. This is the first output. For the input, this is the first output system. And the same system, it is getting another output, stable. And for this input, if the output is this one, this is the input, bounded. This is the output, unbounded. So bounded input, unbounded output. So this is unstable. That what I had shown on the diagram. And the last one, if the signal is like this, also. So it is also producing, for the bounded input, it's producing unbounded output. So that is also example for unstable systems. So I have shown in the diagram input and respect to input and output diagrams. So which one is stable and which one is unstable. So for your better understanding, I will write here. Let us take a signal as like this. T x of t, t x of t. So t x of t, and taking the input signal as like this one. See, this is my input and it is given to a system. It is given to a system, okay, and the system is producing an output. The system is producing an output like this, like this. This is t and this is y of t. See, this is the input and this is the output. See, this is a bounded input. This is a bounded input, and this is also a bounded output. This is also a bounded output. That is, when we give a bounded input to a system, it is producing an bounded output. Then I can say that system is a stable system. So we can say this system as a stable system. Okay, stable system. So this is the clear explanation of what that there in the diagram. So in the diagram, I mixed both input and output in the diagrams. First I have given the input and then I mixed the input and outputs. But here I separately drawn the input and output. So I can take another example. Can you go for another example? Let us take, for the same input, t x of t, for the same input is given to another system. It is producing an output. It is producing an output like this. It's producing an output like this. So this is t, this is y of t. So for this input, the system is producing an output like this. So this input is bounded. This input is bounded, and this is unbounded. So here, for a bounded input, the system is producing an unbounded output. Hence, this system is an unstable system. This is an unstable system. The above is an stable system and the below one is an unstable system. So in the same way, there I had shown different input and output combinations. Okay, in single graph I had both input and output combinations. If you go for the separate one, they will be like this. They will be like this. So for the given diagram, I gone for the clear explanation. Now I hope you all understood the diagram very well, because I shown you the examples here separately. Okay, the next slide we'll go for the problems. Yeah, students, now we will see the problems regarding stable and unstable systems. So I had given 3 examples there. So you have to specify whether they are stable or unstable. So the system equation represents a stable system or unstable system. So how will know that is, if the magnitude of the input signal should be a finite and the magnitude of the output signal should be a finite. That is, the input should be a finite value and the output should be a finite value. If both are finite, then we can say both are bounded. That is, input is bounded and output is bounded. Then I can say it is a Bibo stable. Otherwise, we can say it is an unstable. So consider the first one. So the first one is, so here they had given y of t equal to x square of t. They had given y of t equal to x square of t. Let us take, I have to say the input is a bounded one. Input is a bounded one. That is x of t. Say x of t is bounded. X of t is bounded. That is finite. X of t is a finite value. Now what will be the value of y of t? Y of t equal x of t is a bounded. That is a finite value. Then y of t equal to finite square. Finite square. That is finite value is 5, 10, 15, 900, 500, 600, what it may be, any value. So square of that value will also be a finite. So here for a finite input, I am getting a finite output. For finite input, I am getting a finite output. That is, for a bounded input signal, I am getting a bounded output signal. Hence, it is a Bibo stable. It is a stable. Okay, stable system. The first equation represents a stable system. The system equation represents stable system. Now move on to the second one. Move on to the second one. Simple. How the second one will explain? Here they are given y of t equal to x of t minus 2. Y of t equal to x of t minus 2. Okay, y of t equal to x of t minus 2. Now see, here also let us take x of t having a like. So I will explain this graphically, then you will have a clear idea. Let us take x of t signal is like this. This is x of t. Say this is x of t. Okay, x of t is like that. Okay, now what is x of t minus 2? This is 0, 1, 2, 3, 4, so on. And what is the x of 2? X of t minus 2. So x of t minus 2 will be like this. So 0, 1, 2. So the waveform starts from here. 1, 2. The waveform starts from here. And the magnitude is same. And it will be the same. Okay. Let's say this is the input. This is the input. Consider this as an input. So 1, 2, 3, 4. 1, 2, 3, 4. Okay. 4, 5, 6. See? Yeah. 2, 3, 4, 5, 6. See, this is x of t and this is x of t minus 2. See, both are finite. So this is amplitude finite. Here also it is finite. That it is shifted, just shifted. So here x of t is finite. Then x of t minus 2 is also finite. X of t minus 2 is also finite. So this x of t minus 2 is nothing but our y of t. So this is our y of t. So here y of t equal to x of t minus 2. X of t minus 2. Clear? Okay. Now y of t equal to x of t minus 2. This is for x of t and this is for x of t minus 2. Okay. This is an bounded input. This is also an bounded, which is an output. So this is bounded input and this is a bounded output. For a bounded input, I am getting a bounded output. So I can say this is also a bounded input, bounded output, stable, be both stable. So this is an example for stable system. Example for stable system. Now move on to the third one. Move on to the third one. The last one. Simple here. Y of t equal to e power x of t. E power x of t. And that given mod of x of t value is less than or equal to 8. Mod of x of t value is less than or equal to 8. See, mod of x of t is less than or equal to 8 means that x of t value. So minus x of t to plus x of t. So minus x of t to plus x of t means, so this value is nearly from minus 8 to plus 8. Okay, minus x of t, minus 8, minus 7, minus 6, minus, and plus x of t, that is plus 8. So x of t values is from so on. Now what will be the output? So see here, the output y of t equal to e power x values are from minus 8 to plus 8. Let us take, if it is 8, then it will become as e power 8, or if it is minus 8, we can go for y of t equal to power minus 8 or minus 7, 5. Okay, everything is a finite value. This is a finite, this is a finite, or simply you can write like this: e power 8 or e power minus 8 less than or equal to y of t less than or equal to e power 8. You can write like this. Okay, based on this one, because this is x of t is less than or equal to 8, that is from minus 8 to plus 8. So e power minus 8 less than or equal to this one is output of y of t, which is less than or equal to e power 8. So in this range we have a finite values. So all the values in this range are finite. All the values in this range are finite. So for this is also finite. Minus 8 to plus 8 is a finite, and e power minus 8 to e power plus 8 is also a finite. That is, for a finite input I am getting finite output. That is, for a bounded input I am getting bounded output. So we can say this is also a stable system. Can also say this as a stable system. Okay, so in this way you can do more problems also. I will give some more problems for you. In the previous slide I did 3 problems. Now I am going for another 4 problems here for your better understanding. So here I had given the examples as y of n equal to x of n plus 3. Yeah, see, up to now I explained you in terms of continuous time variable t. Continuous time variable t. I said x of t, y of t. So the same explanation you can go through for discrete time variable n also. Discrete time variable n also. That is, for discrete time variable also the concept is same. The concept is same. If the input signal, the discrete time input signal is bounded, for that the system produces a discrete time output signal which is also bounded, then I can say that system is a BIBO stable system. Simple. So there is no need to explain the discrete once again. Here for discrete also the concept is same. Okay, so replace the continuous time variable t with the discrete time variable n. So there I had gone for x of t as an input signal and y of t as the output signal. For discrete you can take x of n as the input signal and y of n as the output signal. See, if x of n is a finite value, then we can say it is a bounded value. That is, the magnitude of the value, the amplitude of the value, the discrete time signal amplitude or magnitude is finite. Then we can say that is a bounded signal. Okay, and if you give that bounded signal as an input to a system, the system will produce another signal as output. If that produced output signal is also a finite one and it is a bounded signal, then we can say that system is a stable system, BIBO stable. That is, bounded input, bounded output. Okay, simply. So the equations, everything are same. Only for continuous and discrete we will get the changes only by one point. That is, in continuous we will get integration, whereas in discrete we get summation. This is the only difference. Whenever we get integration in continuous, for discrete we will get the summation. Because integration is nothing but the addition. Summation is also nothing but the addition. Both are same. But for representing, whenever we go on for the continuous time variables, we will use the symbol integration. Whenever we go on for the discrete time variable, we will go for the summation. Okay. So this is the only difference for continuous and discrete as per now. So here either continuous or discrete, the signal is anything. If a continuous or discrete signal which is at the input is bounded and that is given to a system, if the system produces an output, either it is a continuous or discrete which is also a bounded, then I can say that system is a BIBO stable, bounded input, bounded output, stable system, simply stable system. If it does not produce a bounded output at the bounded output, then the system is unstable. Okay, so it is stable, otherwise it is unstable. Only two cases, stable, unstable. Okay, so why I explain all this means, because here in this problem you got y of n equal to x of n plus 3, where if you treat that n as a discrete variable, then y of n will be equal to x of n plus 3. It represents a discrete time system. So while explaining theory, I explained everything with respect to the continuous time. It is x of t and y of t. Here we have y of n and x of n. So for that reason I gave the explanation here. Okay, only the thing we have to do is we have to replace the variable t with n. the small t will be replaced with small n. Then the continuous concepts will convert to the discrete concepts for this. Okay, for this. So I am not explaining right from the start. I had given a briefing of what a discrete stable system and discrete unstable system. Okay, so for discrete or continuous, if the bounded input produces a bounded output, then it is stable. If the bounded input produces an unbounded output, then it is unstable. So this is for either discrete or continuous. Now coming to the example. Now coming to this example. So what they had given? They had given y of n. They had given y of n equal to x of n plus 3. They had given y of n equal to x of n plus 3. So it represents a discrete time system. Okay, we have to find out whether the discrete time system is stable or unstable. So how we will find out? First, I have to consider the input should be a bounded. That is, let us consider the input as a finite one. The input as a finite one. So here the input is in the system. Y of n is the output. X of n is the input. So the input signal representation of a discrete time system is x of n, and the output signal representation of a discrete time system is y of n. I explained at the beginning of I am explaining discrete and continuous time systems. Okay, so this is the representation of output signal of a discrete time system, and this is the representation of input signal of a discrete time system. Okay, so here the input is x of n. Let us consider the input x of n is finite, less than infinity, a finite value. That means it is a bounded one. It is a bounded one. Okay, clear? This is a bounded one. Now, how can you get y of n? So y of n will be equal to x of n. X of n is finite value plus 3. See, you can take any finite value. Either you can take 5, 10, 20, 30, 100, 500, whatever it may be. If you take a finite value, if you add 3 to that finite value, the answer will also be a finite. The answer will also be a finite. Simple. So take 100. 100 plus 3, 103. 10,000. 10,000 plus 3, 10,003. Any value. If you take any finite value and add some plus 3 to that one, add 3 to that one, the answer will also be a finite. So here, as input is a finite, that is bounded, the output y of n is also finite. The output y of n is also finite, that is bounded. It is also bounded. So what we can say? This is a bounded input, bounded output, stable. That is, as the input is a finite and the output is also finite. That is, input is bounded as well as output is also bounded. Okay. So we can say this system as a stable system. We can say this system as a stable system. Is it clear? So first one. So y of n equal to x of n plus 3. Simple. So I have to consider input as a bounded one. So input is a finite value. If I add a 3 to that finite value, the answer will also be a finite. That means the output will also be a finite. That is, output is also a bounded. As the input is bounded and the output is bounded, so the system is bounded input, bounded output, stable. So the given system is a stable system. Okay. Now move on to the next one. So the next one. So up to now we saw all the systems are the bounded systems. Now come to this one. Come to this one. The next one is y of t equal to t into x of t. T into x of t. See, here x of t is the input signal and t is the variable. T is the variable quantity. Only the input is x of t. Okay. So in this case, I have to consider a bounded input. That is, input is a finite, as I explained in the previous problem. That is, here, first of all, whether it is a discrete time signal or continuous time signal. X of t equal to t, y of t equal to t into x of t. Y of t equal to t into x of t is a continuous time signal. So it represents a continuous time system. So we have to say whether this continuous time system is stable or unstable. The concept is same. Now, this y of t. Now this y of t equal to t into x of t. Here y of t is the output signal and x of t is the input signal. So to check whether it is a stable or unstable, what to consider? I am considering the x of t as a finite value. X of t as a finite value. Consider x of t is finite. Finite. Okay, it is bounded. Bounded. X of t is finite. Okay. Find value anything, any value. So minus infinity plus infinity, inside that less than infinity. You can take any value less than infinity here. Okay. Now y of t equal to the variable t should be multiplied with a finite value. Okay. If here, if the variable t is infinite, if the variable t is infinite, because I consider only x of t is finite, not about t. The total signal, t is the variable and x of t is the complete signal. So even though if t is infinite, x of infinity is some finite value, there is a function like that. If you think there is a function like that. So here, if this x of t is finite, but the variable t is infinite. If the variable t is infinite, let us consider it is infinite. Infinite is multiplied by a finite value. So finite value is 50 and infinity is multiplied with 50. What will get? I will get infinity. Infinity. So here the system output is infinite. System output is infinite. As the system is producing an infinite output, that is, the output is not bounded. So here this is infinite. Infinite. That is unbounded. That is unbounded. So here the output is unbounded for a given bounded input x of t. The y of t, the output is unbounded for a given bounded input x of t. So the system is producing an unbounded output for a bounded input. The system is said to be unstable. The system is said to be unstable. So this is the example for unstable system. So simply we can understand this is unstable by doing on like this. Now moving on to the next one. Next one. So here the next one is y of t equal to x of t into sin t. X of t into sin t. Simple. So we have to check whether this continuous time system is an stable system or unstable system. How can you find out? How can you find out? Simply here also the input is this one. X of t is input, not sin t. Sin t is the variable. So the system work is, what the system will do? The system will multiply the input with sin t. That is the function of the system. The function of the system is, what the system will do? System will multiply the input signal with sin t. So whatever the input signal is, if we give another one as an input signal, so the system will multiply that input signal with sin t. That is the function of the system. So here this is the input signal and this sin t is our variable. Okay. Now let us consider this x of t is finite. X of t is finite. Okay. We have to consider this as a finite value. It is a bounded. We have to consider this as a bounded. Clear. Now y of t equal to, now y of t equal to this finite value into sin t, Now what are the maximum values of that is produced by a sine function? The maximum value that is produced by a sine function is 1 plus 1, and the minimum value that is produced by a sine function is minimum value minus 1. That is, the sine function will have the values from minus 1 to plus 1. The sine, that is the sine function, inside we have anything. Okay, you can write anything. The sine function will have a values between minus 1 and plus 1. Okay, so the minimum value is minus 1 and the maximum value is plus 1. So the sine value will have a values between these two only, between these two only. Okay, these two they will have, that is the minimum value, that is the function. Minus 1 is less than that sine function, and sine function is less than or equal to this one. So you can write this less than or equal to the function value, the sine function. So based on this value, we will get values between these two, that is minus 1 less than or equal to sine of. So based on the value, okay, there are some values in between these two only, minus 1 to plus 1. Now this y of t equal to the finite multiplied by sine value. Minimum is minus 1, maximum is plus 1. So it should be multiplied the values between minus 1 to plus 1 for all t, minus 1 to plus t. So all these are the values between minus 1 to finite are finite, simply they are finite values. Okay, finite values. So finite multiplied by a finite, 3 into 9, 27, 4 into 5, 20. So if you multiply two finite values, the answer will be a finite, that is output is a finite value. Finite means it is also bounded, okay. So for the bounded input signal, the system is producing a bounded output. So the system is bounded input, bounded output, be both stable. The system is stable system. You can say simple. Here x of t is a finite, and sine t values shouldn't, the minimum value of the sine function is minus 1 and the maximum value is plus 1. So the sine function will have the values between minus 1 and plus 1. So the values between minus 1 and plus 1 are the finite values. So the finite value of the input is multiplied with the finite values between minus 1 to plus 1. That is finite into finite. That is 9 into 3 or 2 into 6 or 7 into 5, whatever it may be. So if you multiply two finite values, the answer will be a finite. That is the output is a bounded one. As the output is a bounded for a given bounded input, so the system we can call it as a stable system. Yeah. Now move on to the last one. So here I have taken the last one as y of n equal to x of n by sine n. So this is the function, that system function they had given. So system equation. Now say this system equation is a continuous or discrete. This is y of n. So you can say it is discrete. So for your better understanding, here I had taken a continuous time equation. Here I have taken a discrete time equation using y of t, x of t and sine. Okay, y, x and sine. Here I termed as y of t equal to x of t into sine t. Here y of n equal to x of n by sine n. So one is for continuous, another one is discrete. Just for your understanding that the concept is same for continuous as well as discrete. Only the change is the variable t. Here the variable t only changes. Okay. Now see, first of all consider the input x of n is finite, that is bounded. So here the input is a finite value and it is bounded. Okay. Now the output y of n. Y of n equal to x of n. That is a finite value. By sine n, which is equal to finite by sine n. So y of n is nothing but the finite value by sine n. Now I treated this as a bounded one, finite value. Now the sine function will have the values between minus 1 to plus 1. We all know the sine function will have a values between -1 to +1. So this is the range of the sine function. Range of this sine function. Inside this function, sine of anything should be between -1 to +1. That is, -1 is less than or equal to, sine function is less than or equal to +1. Okay, I already explained you. Now see -1. Next, let us take -0.9, -0.8, so on, -0.1, and then 0. 0.1, 0.2, 0.3, and so on 1. Okay, so between -1 to +1 there is a term 0. For some function of sine, that is sine of something, sine of some value, if for a particular value of n, sine of particular value of n, I will get, there is a possibility to get the value as 0. Then the output will become as, at that case, y of n equal to finite divided by 0. At this case, at a particular time instant, so at a particular instant of that value, so at sine of that value the answer is 0. So I will get finite by 0. Finite is 9 by 0, 9 by 0, the finite value by 0. Anything by 0 is nothing but infinite, infinity. So answer is infinity. Here the output is infinite, that is unbounded, because it is infinite, not a finite value. It is not a finite value, that is infinite. So it is unbounded. So I already said, for all values, for each and every time instant, each and every sample of the input, the system has to produce a bounded output. For one time instant or a one time sample, if the system does not produce a bounded output, then the system is an unstable system. So here, for all the remaining values except 0, from -1 to +1, for all the remaining values, y of n is finite by finite is a finite. But for one sample, that is for one value, the sine function will go as 0. So for one value of n, okay, the sine function will go as 0 for one value. Even for that value also, for one value, it is sines of that value will be equal to 0. So finite by 0 is infinite. For one value, it is giving infinite, that is, it is producing an infinite value for one sample, even though we have to say that it as an unbounded, because for each and every sample it has to produce bounded output. For each and every time instant, if it is a continuous, we can say like time instant, for each and every time instant the bounded input has to produce bounded output. Even for one instant of bounded input, if it is producing a unbounded output, then we can say that as an unstable. So for that reason, as for this, whenever this sine function will goes as 0, finite by 0 is infinity, the output is unbounded. For one instant it is giving unbounded, that means it is unstable. It is unstable. Okay, so this is how we will go for stable and unstable systems. Okay, we can find out if they given any equation. So based on this, we can go whether that is a stable system or an unstable system. Or I can give you more examples for unstable also. So unstable, we can go for y of t equal to integral of x of t dt. It is an unstable. Y of t equal to d of x of t by dt. It is an unstable system. So integration, differentiations. Okay, so these are all these y of t equal to integral x of t dt, y of t equal to d of x of t by dt. These are all the examples for this unstable systems. Okay, so this is the explanation regarding stable and unstable. So previously also I had given 3 problems regarding stable. Here also I had given 2 for stable and 2 for unstable, and had some more unstables. So I had given graphical representations, and I had shown the graphical representation how a stable system will look like, and how an unstable system will look like, and how a bounded signal will be, and how an unbounded signal will be. And finally given so many example problems for your better understanding. So with this, I will finish the topic. Stable and unstable systems. So this is the topic regarding stable and unstable systems. Okay. So what is the next topic? What will be the next topic? So the next topic is it is nothing but invertible and non-invertible systems. The last one in the classification of systems is invertible and non-invertible systems. So we will go through the invertible and non-invertible systems. Okay.